organizing these talks, and I've been following along with the titles, but not necessarily attending all of them. And I'll tell you, this talk has a little bit less of the ocean in it than prior talks in the session. I would say the target audience would be people who are concerned about coastal flooding in the near future and far future, but the perspective I will take is from the atmosphere. The title of the talk you can see there, and this was put together by research that I did with a PhD student in my group, Katherine Towey. There's also some collaborators who inspired some of the work or participated in some of the work that I'll show. The figure that you can see there as the path for a extratropical cyclone in 1950 that created a record-setting surge for New York City, and then Hurricane Sandy, which most of us are familiar with, which caused record-breaking surge in New York City in 2012. Both of the tracks have a very particular aspect to them, which is as they go north, they pull to the west, and the fact that they caused really strong surge is not a coincidence. And Tim Hall at GISS has done some work on the uniqueness of Hurricane Sandy, and I can tell you from our own work that the Great Appalachian Storm is nearly as unique. Maybe in the future, Tim and I can actually use the track model and look at the same thing for that. Welcome everybody. If you're from the East Coast, or if you're on the West Coast, good morning. Let's start with simple definitions, get everybody on the same page. So we want to think about storm surge and storm tide. Storm surge is the difference between what's measured and the tide. On this particular figure here, you're also seeing a wave, and just keep in mind that the waves are separate from the surge. Timescales of the waves, something like 30-second. Timescale of the surge, more like 6 to 12 hours. I'll be talking today mostly about storm surge, and it is not a good metric for flooding events, but it is a good metric for measuring the size of storm forcing, right? So we just want to keep in mind that I'm removing the tide when I'm talking about what's going on. Before I get into that, I will show some results talking about storm tide, because storm tide is more relevant for flooding, okay? And so that is the storm surge plus the tide. I'm putting these in mostly for completeness and to emphasize to everyone that there is a good understanding about what's happening with flooding. The flooding trends are increasing. There's many papers showing this for the East Coast. This particular example is from a Talca et al. Study. They put together water level data for the New York City region for multiple different locations. Then this particular case documented the annual maxima storm tide and used statistics to show that there is definitely an upward trend and that it's not just caused by Sandy. The visualization of the trend can be seen in the below figure, especially this red, where you're looking at the upper 25th percentile for a 36-year running average of the annual maxima storm tide. So you see this trend with the strongest storm tides increasing with time. Big summary of what we know: coastal flooding is increasing. Some examples to get you background on that if you're interested. The change in flooding for most locations is attributable to sea level rise. Looks like there's some background noise, so if anybody's joined and has their mic on, just go ahead and mute, please. There's also natural variability in the system, and it has a very strong signal in the storm tide record. This is shown in this Wall and Chambers 2016 paper. And of course, the model projections show that coastal flooding will increase. I've just picked a few examples of these, some recent, including the talk last week where we saw that very nicely from Jianjin. So sea level rises, flooding gets worse. There's no confusion about this. The storms also change. What we don't know is how this exactly impacts the surge characteristics. This issue of a strong signal in natural variability in storm tide might be related to changes in storms, but it might also be related to changes in the low frequency forcing of storm tide, such as the characteristics of the ocean on decadal timescales. Now, from Tim Hall's work with Jim Cawson, we know, for instance, that tropical cyclones are stalling more and producing more rain. Their study did not get into the details of surge, and so this is part of the motivation for what I'm digging into here. What causes storm surge? Well, when you're piling up water on the coast, it's usually because you have winds that are blowing the water towards the coast, or the winds are generating waves that are helping to pile up the water. We know that the atmospheric low pressure associated with a cyclone allows the water to rise locally. This is the inverse barometer effect. The idea of rain affecting it was mentioned by Jianjin last week. And actually, I'm gonna end the show for a second, and I'm going to stop sharing screen to ask others, just to keep it a little more interactive. Has anybody else seen this? Is it the rain mattering? I mean, maybe for the Gulf of Mexico, when you get these giant TC events, that makes a lot of sense. I had never thought about that before. Had anybody else?
Brown ocean, you mean?
No, the rain actually being
like
enough.
The brown, but around the Gulf Coast, the brown ocean. The
Yeah,
fact that you didn't get a die down of the storm intensity when it came onto land because there was such an inundation that the land was kind of a marsh.
Okay. No, I was thinking of the idea of the measured water level actually being higher because of accumulation of precipitation. Is Jean on the call? Jean, is that? Maybe he's not.
And you specifically mean out at sea, right? I mean, we know that it happens in the estuaries, but yeah, and it struck me as surprising too. I think I've heard of it, but yeah, we don't think about it a lot of the time. But
yeah,
good question.
That's interesting. Yeah, it's for extratropicals, I've completely ignored it, but I could definitely see in the TCs worrying about this. All right, so back to screen share. Just keeping you all awake.
Gavin just wrote a comment in the chat saying that that this is included in the GISS model.
Okay, very interesting. Thanks. So typically, you got tropical or extratropical cyclones generating the surge. There are cases when you just have a strong atmospheric pressure gradient. In terms of the cyclones, we can track them by following the pressure minimum or local relative vorticity maxima near the surface. And then we can look at the latitude, longitude position of the tracks versus time. And in this example from Cully 2010, they're plotting the tropical cyclone tracks that cause all the surge greater than 0.6 meters for New York City. I'll come back to this type of figure later on. Cully concluded that both extratropical and tropical cyclones were important. However, the Orton et al. Study showed that for New York City, the hurricanes create more of the strongest surge, and for the extreme surge, the TCs are distinct in terms of their forcing from extratropical cyclones.
Sorry to interrupt. So Allegra is asking a question on the chat relating to the rain, I believe.
Okay.
Jimmy, do you just mean that when you saying the extra rain, you just mean that ocean has a free surface and not a rigid lid? So you're just adding water on top? Is that what you mean? Or are you meaning something more like you have this freshwater lensing effect, and so you can more easily heat the surface ocean and reinforce intensification this way? I'm not sure I exactly follow what you're meaning.
I don't have a strong intuition about it. In the talk last week, it was mentioned that the in the model, the projected, or not even the projected, the storms in the historical record that were creating strong surge also were stalling near the coast and raining a lot, and this was supplementing the surge. And so it wasn't clear for me which side of that Jianjin was pushing it. So yeah,
he just meant like a direct impact of, you have coastal inundation, but then you also have regular old flooding from rainwater.
Okay. Yeah.
Is that what you're saying? I don't know. Last
I don't
week
know what she meant.
Map deadline, and I did not come last week. I'm sorry.
It's all right. No, I'm not sure what she meant. But I mean, it feels more like the flooding would be intensified by the on-land rain rather than imagining that the precipitation locally would have any impact on the water levels.
It's a good research question, Jimmy. And I mean, there'd be a barotropic response that would happen more quickly and a baroclinic response, and you'll have a steric effect, which is, I think Gavin just said. And it struck me as surprising. And I think it'd be, if somebody knows of a paper on direct rainfall influence on sea level offshore in the ocean, you know, or on storm surge, then maybe post it for everyone to see. I think it's a good question. And I think it's a minor effect. The barotropic response would be pretty fast, and unless you're dumping 10 inches of rain, which you could be in a 2 hours or something, then it certainly shouldn't have an effect. You know, the wind-driven effect's much faster in terms of inches per hour, for example, or and the inverse barometer could be faster, but it could be significant. I just haven't seen it.
All right. No, thanks Allegra and Philip. So visualizing an extratropical cyclone surge event is the topic of this slide. And in the top left, you have color shading for wind strength, and then the contours showing sea level pressure, and the wind direction would be roughly parallel to these contours. And because this is a low here, it's going to be counterclockwise. Therefore, the water is being directed by the wind towards the flood region or towards the large surge region. For this particular case, I plotted the time series of surge at 3 locations: Cape May, New Jersey, the Battery in New York City, and Bridgeport, Connecticut, showing how, as this storm migrated along, the surge maxima at the different regions occurred at different times. You can also get an idea of the time scale for this surge event. And then I'm also plotting the track for this surge event, and this is not an error. This particular extratropical cyclone was stifled by anticyclone upstream, which allowed it to really just kind of hang out and do a lot of advection of atmospheric mass, and therefore also creating wind stress, which would have been driving the water inland. For those who maybe are wondering what is this extratropical cyclone, these are the most common weather maker in New York City. They have surface temperature fronts. You see about whenever the people on the news are talking about the fronts, they're talking about an extratropical cyclone. Subsets of extratropical cyclones are nor'easters as well as bomb cyclones, and I'll talk a little more about them later. A question that I ask myself regularly is, do we need cyclone information? For the New York City region, we can make a reasonably good statistical model of surge in which we're just using some atmospheric information. And separately, we have plenty of ocean models that don't require track information. They just require wind and pressure information to drive them. The Roberts et al. Study in 2015 used this region here, this blue box, and then they tried different size boxes and found the optimal size box and then the optimal integrated time of wind stress to drive their statistical model of surge. They also have sea level pressure as an additional predictor. And I like this to think of it in a really simplified manner where you can say what information from the atmosphere matters for surge versus what do the cyclone tracks provide. And these arrows are intentionally confusing, which is to say that it's not a one-to-one match between the information that the ocean needs from the atmosphere as opposed to what we get from cyclones. So why spend all of these times with cyclone tracks? Well, my opinion is for tropical cyclones and extratropical cyclones, weather model prediction of tracks are more robust than those of strength. So if we have a statistical intuition of what the tracks are doing for surge, that might actually buy us more time in terms of medium range predictability. With the track analysis, we can do probabilistic work, like which Tim Hall has been doing. It's been shown that the track information is useful for GCM evaluation. And then what I call GCM projections using statistical downscaling, which is when you link the large features, which are easier for the GCMs to capture, to the hazards, then you can use the large scale features to monitor potential changes in the hazards. And then I've listed here some longer or larger scope questions that this work that I'm doing now is eventually, I hope, going to help answer. I've mentioned the first. The second would be on seasonal forecast timescales. We want to link the track characteristics to large scale natural climate variability, and then have another method of kind of building a bridge from the natural climate variability back to surge. And then on climate timescales, we can just ask the question, does storm variability even matter? Right? I mean, if we know within some uncertainty how sea level will rise, could we perhaps take the storm variability out of the equation completely if we know that it's just kind of flapping around in the wind? That's a bad analogy. All right, so today's research questions will be, what are the relative roles of tropical cyclones and extratropical cyclones in generating strong surge along the East Coast? And for this analysis, we'll identify the strongest surge events and then sort the surge events using cyclone information. And then in the second part, I want to ask the question, can variability in the strongest storm surge events be explained by variability in the characteristics of the storms that cause the surge? And so in this case, instead, we're going to say, identify all cyclones that travel near a region and then sort the cyclones based on their properties. All right, so for those that joined late, there's a little bit of feedback, so everybody just make sure to mute your mics. All right, so in analysis one, we will take the tide and current data. And I make a note that if you go and grab this data, be careful for New York City. Around World War II, there's just an issue on timing of the tides. My work is starting after this to avoid this issue. For cyclone data, we'll use hurricane track data, which is HRDAT. For the extratropical cyclones, I track the data myself in a reanalysis data set, and I'm using an algorithm developed by Mike Bauer at GIST. And then the algorithm that I'll be using in the analysis of the surge is to identify the largest surge events, isolate those that are within 2 days, so I just have a single maxima, I'm not double counting. For the date of the surge, find the closest cyclones. And if there's multiple cyclones present, I have methods to make sure I attribute the correct cyclone to the surge. The region that I'll be using for this first study is the mid-Atlantic and Northeast US. So I have sites spanning from Portland, Maine down to Duck, North Carolina. For these sites, we calculated the 1 year and 3 year return levels. Because we were looking at data from 79 to 2014, we felt like these were reasonable return levels to calculate with our data set. Since that time, Lin et al. Has calculated return levels for ETCs only for some East Coast sites. So if you're interested in return levels, this is another paper to look at. All right, so how do the big events compare for tropical and extratropical cyclones? And here we're going to define our big events as storms that cause surge to exceed a 1 year return level at 3 adjacent stations. And I'm showing here stations to the north, stations around New York City, and then stations to the south. And so what we do is we plot the actual surge value for the stations. We rank them by the average of the 3. And then we color code this by whether they are tropical cyclones in red or extratropical cyclones in blue. And Sandy is here, standing out in terms of its size. However, overall, you can see it's generally weak linear increase in terms of the strengths in these ranked events. And you can see a relatively equal contribution from tropical and extratropical cyclones to these strong surge events. Next, we wanted to ask, well, for individual stations, what is the role or relative role of tropical cyclones in causing the strongest surge? So the idea is that for a given station like Duck, North Carolina, we rank surge events and then we find out what percentage of the surge events were caused by tropical cyclones. So for the top 10 events in Duck, 60% were caused by tropical cyclones. Same is true for Sewell's Point, Virginia. For Battery, 30% of the top 10 events were caused by tropical cyclones. And then you can see these numbers drop off. And when you get to something like the top 50, none of the regions have more contribution from tropical cyclones than extratropicals. This is a reflection of the tropical cyclones being more rare than extratropical cyclones. The dash versus solid is separating those at New York City or south or north versus those south of New York City. And so this is Newport, Rhode Island stands out. And as a reminder, Newport, Rhode Island is sitting here. So on the coast, it's in an interesting location compared to the others. And it turns out that in this location, it's actually able to avoid or have less of an impact from extratropicals than some of the others. We did counting for it, and it's not that it has more tropical cyclones, which was what I used to assume, but it's actually because Newport, Rhode Island avoids a lot of the big extratropical cyclones. One might wonder if the duration of surge differs for tropical and extratropical cyclones. So what we do here is we plot the number of days that surge is continuously above 0.4 meters. We've also looked at this for for 0.5 meters and 0.6 meters, and the story is the same. So we're just plotting here time continuously above some threshold versus the maximum surge strength, and then color coding them by pink showing those that are tropical cyclones and black showing other, which would be extratropical cyclones. I note this one here, which is off the chart in terms of its duration. And this is another one of these extratropical cyclones whose path is suspiciously zonal. Once again, it was inhibited by an upstream anticyclone. If we want to look at probabilities, we can drop a circle around New York City for different radii and then ask the question, how many hurricanes came in this region? How many tropical cyclones came in this region? How many extratropical cyclones came in this region? So if we just start up here with the first column and just look at this number. So we have 7 hurricanes since 1946 that came within 200 kilometers of New York City, as compared to 19 tropical cyclones of any strength and 266 extratropical cyclones. But if instead of counting the sheer number of events, we ask how many hit an exceedance, a surge of 1.25 meters, well, almost 50% of the hurricanes do, whereas not even 1% of the extratropical cyclones do. Interestingly, for the extratropical cyclones, as we move farther away for this really strong surge, we actually increase our likelihood of causing the strong surge. Also of note from this is that for all tropical cyclones within 800 kilometers, you have about a 16% or 17% chance of causing a surge exceeding 5 meters. And that's the same for extratropical cyclones. So at some point, things start to catch up. But for the most extreme, we're reinforcing or affirming the result from the Orton et al. Study about the influence of the hurricanes. Now we're going to use this type of table to step back and say, well, in this next analysis, let's just find all cyclones that travel near a location and then examine the surge and cyclone characteristics. So this is using this extended time period. The TC tracks are still heard at. For extratropical cyclones, I use a combination of the ERA 20 and ERA interim reanalysis. We'll find all of the storms within some distance. I use a larger distance for ETCs because their wind footprint tends to be larger. For each cyclone, we'll find a maximum surge within some window. And so this means, if the cyclone is here when the maximum surge occurs, that's okay. We're going to link those up as one. And then we're going to test for relationships between the cyclones and the surge. Yeah, so most of the results I'll show are from New York City, but we've replicated them for Newport, Rhode Island, Sandy Hook, New Jersey, and Cape May, New Jersey. The ones that don't replicate nicely, I will show the results. A little more background information. So in terms of what determines storm surge, for New York City, there was a study from Lin et al. Showing if they use synthetic tracks to drive a numerical model, they get what appears to be a quadratic relationship with a lot of noise, okay? But some relationship between the wind strength and the surge amount. However, we also know that in addition to tropical cyclone wind, the tropical cyclone size matters. And this has been shown for observations for the Gulf of Mexico. This is Irish et al., where they're plotting hurricane size, defined as the radius of maximum wind, versus a normalized surge, where they're accounting for the inverse barometer effect. And they're showing there is some relationship between size. And so this, I think we can relate back to wind fetch, or the distance along which the wind is blowing in the same direction, which we could also think of as terms of the persistence of the wind. The Irish et al. Study was for the Gulf of Mexico, and they also emphasized the bottom slope is key. And in every part of this talk, I'm not addressing the fact that the geometry of the coastline and the bathymetry of the bays matter. We're just trying here to see as much as we can get from the atmosphere. I will note that for my analysis of tropical cyclones, I'll focus on sea level pressure and maximum wind. The sea level pressure gives some indication of both wind strength and storm size. It's not ideal. For tropical cyclone size, for the Quickscat era, we actually have some consistent or robust estimate of tropical cyclone size. Beyond that, it might be the case that a little more work is needed before we can have one metric that fits all. All right, so here we go. Diving into the data, we say, all right, take all the cyclones, tropical cyclones that pass near New York City, and then plot the surge they generated versus the distance to New York versus storm sea level pressures and storm wind. All right, and I plot these first of all with no fits on them to give everybody a chance to do whatever you want in terms of how you would construct this data. I would say for us, we focused in on the distance first. You can see, especially for wind, it's a little disheartening in terms of what you're getting, but it gets better. I also note for older events, sometimes this SLP and max wind data is not available. Now I'm going to take the distance versus surge plot, so the same one we just saw, and I'm going to color code the points by the storm's central pressure minimum. And the idea is that we would like it if the higher central pressure, meaning a weaker storm, tends to be for the weaker surge, and that when we have deeper surge, we also have deeper sea level pressures. It works out sometimes. There are cases where it does not. I'll mention also these two cases where you had very strong surge at a far distance turn out to be somewhat unique storms. The blue one is Hurricane Wilma in 2005, which was very deep, the deepest storm ever when it was down in the Gulf of Mexico. And then as it moved out, it became very large and merged with an extratropical cyclone. The other storm, this red one, this actually, the track starts here and then comes down to the south and then wraps back out. And so this was a tropical cyclone that merged with an extratropical cyclone and another tropical cyclone, and they made a movie about it called The Perfect Storm. Let's go back to trying to find relationships between surge and the hurricane strength. This is a plot you've seen before. I've now put linear fit and a Pearson correlation coefficient on both of these. Not so much for predictability. However, if we limit ourselves to the tropical cyclones that are within 500 kilometers of New York City, now the relationship with sea level pressure and the relationship with wind starts to improve a little bit. If we limit ourselves to the storms that are within 250 kilometers of New York City, now suddenly we start to see a relationship in terms of both sea level pressure and wind. For sea level pressure, we could maybe think about the inverse barometer effect, which is an approximate 0.01 meter rise for 1 hectopascal drop. So you'd get something like a ½ meter for 50 hectopascals. So it's not enough to explain this line, but it's probably there. The SLP and winds are of course correlated. So whenever the SLP is deepening, you're likely getting stronger winds. For the wind relationship, although it's not as strong in terms of the correlation as sea level pressure, a lot of that is because of this storm over here, which is seemingly very strong, but creating a very small surge. And if you look at this storm track, it's very unique. So this is Esther, which turned away from New York City. It created a lot of problems for Rhode Island, but not so much for New York. If I take out Esther, we now have a similar correlative result between wind and sea level pressure, or wind and surge is what we saw over here. I'll note a quadratic fit works here as well, which would be consistent with the Lin et al. Study. If we turn our attention to the paths, which gets back to this idea of getting some sort of predictability, what I do now is I consider only hurricanes, so the strongest in terms of winds because they're designated as hurricanes, that came within 500 kilometers of New York City, and I sort those into those creating large surge, moderate surge, and small surge, which I just define. These are not technical definitions. But what's really great is the difference in the track characteristics for the smallest surge and the largest surge, right? So there's a clear need for hurricanes to pass close to the region of impact. You say, well, this might just be something unique about New York City, so what happens elsewhere? If we move to Newport, Rhode Island, so the center of our circle has changed now. The cyclones involved has slightly changed, but again, the largest surge causing events and the smallest surge causing events have very distinct differences in terms of their path. If we move south of New York City to Cape May, things are a little bit messier. Certainly those that are within 500 kilometers that cause the weakest surge are not coming close to the point of impact. And I'll note I've switched the cutoff from 1.5 meter to 0.8 and 0.4 meters. And this is just because if you look back at the return levels for Cape May, they are lower. I wanted it to be consistent with that. For Cape May, there is still this nice predictability of winds for surge when we limit ourselves to the closest events. Moving farther south to Sewell's Point in Norfolk, Virginia, now the strongest surge events also are these events that pass right near or over. The weakest ones are now not as clean. However, it is the case that there is always a eastward component to the track for these weaker ones. So it's coming back to this idea of the path dictating wind direction. For Sewell's, we don't have a nice predictive relationship between storm strength, whether we talk about it in terms of sea level pressure or winds, and surge. And it's made more confusing by the fact that if we look at what sea level pressure is doing and focus in on winds, the strongest wind events are causing small surge. This might be related to the direction, but it might also be something where we want to look at the duration and stalling for this region. So we're going to try and do that next. So the summary for the tropical cyclones. The cyclone center distance to impact location is the most important predictor. The cyclone path is also critical. For tropical cyclones within 250 kilometers, sea level pressure and wind can be very useful predictors, which matches with modeling results. For future work, I really like to determine a robust reanalysis-based tropical cyclone size metric and incorporate this in. So we're working on that. So now we're going to turn our attention to extratropical cyclones. And before I jump into my results, a little more background. So for the Northeast US, Catalano and Broccoli used analysis of the winds, sea level pressure, and upper level geopotential heights to sort storms and then clustered them to find those that cause stronger and weaker surge. And they found that the stronger events were often associated with a large anticyclone to the northeast, which allowed stronger gradients, coupled with the fact that the storm itself moved kind of slowly. So nothing about tracks, but something about the synoptic conditions. For an analysis of extreme surge events in the UK, where they were looking at multiple surge events at different locations, there was some consistency in the track path. You can see all of these tracks were originated over near Newfoundland and tracked almost zonally across or with a weak tilt to arrive and generate a lot of surge. So with that in mind, oh yeah, and then there's another piece of motivation, which is we separately had already done an analysis where we looked at surface winds in the Northeast. So this is the land-based weather stations, and we took all of these, and then we attributed the wind events at these stations to extratropical cyclones and then analyzed the tracks. And so in this case, if we sort from moderately strong wind conditions, which was a 1-year return level exceedance at 5 or more stations, to a stronger condition of a 3-year exceedance, and so on, following the blue arrows, and then go back and follow now the tracks. What you should see is there's a concentration of the path causing the strongest wind events. They take this southwest to northeast. So there's a preferred path for the extratropical cyclones causing the strongest wind events in the northeast. And this can be attributed to the geometry of the extratropical cyclone. And this has nothing to do with the number of tracks that take this path as compared to other paths. So what about for surge? So we find our top 100 surge events at the battery and then sort those into quartiles and then do the same thing we did with wind, where we're trying to find some relationship with tracks. And unlike winds, there's no clear characteristic path for the strongest surge. So let's take this other approach where we find all the tracks that pass near New York City and then analyze them based on cyclone strength and surge. All right, so as a reminder, here's this plot that we saw before for tropical cyclones where it was distance versus surge. Now I'm doing the same thing for extratropical cyclones, right? And from that table earlier, you're prepared for the fact that there was going to be a ton more data as we get into extratropicals. And the search radius is larger than for TCs. This is because the extratropical cyclones tend to have a larger wind footprint. Color is sorting these by sea level pressure. And so what is nice, at least, is that there is this overall tendency for the yellow, which is the less deep cyclone, to have much lower surge than those that are the deeper cyclones. We can limit ourselves to those that are closest and then look at wind strength. And for extratropical cyclones, we're going to use the cyclone average 900 hectopascal wind speed. So 925 hectopascals is roughly between, I would say 500 and 800 meters above the surface. However, it has less bias than the surface winds in reanalyses, simply because it just it deals with less influence from the surface parameterization. We're doing the same exercise as before, where we consider all of the storms and look at surge versus wind strength, and then conditionally sort to those that are closer and closer to our impact region. And as we move closer, the correlative relationship improves, suggesting, okay, once we worry about the tracks that are closer to our impact region, suddenly we are able to match observations with expectation of the wind having some sort of predictive effect for surge. Inspired by the Lin et al. Result, we also looked at these in terms of a quadratic fit. And so now it's the wind again on the x-axis and surge, and then color-coded by the strength of the SLP to see if we get additive predictability from the sea level pressure. The idea being that when it's deeper sea level pressure, we are seeing stronger surge. Now, overall, the color follows the x-axis because there is this correlation between sea level pressure and wind. However, if you fix your eyes on a given wind strength, there is this nice relationship with surge between the strength of sea level pressure, or the depth of sea level pressure, and surge. All right, so as with tropical cyclones, we want to ask if details of the path matter when we limit ourselves to the closest, the surges, the tracks that pass closest to our region of impact. So we're sorting the tracks that pass within 100 kilometers of New York City into the strongest and the moderate and weakest. And what you can see is that not much going on here in terms of track pattern. We move the circle out to 250 kilometers and redo. And now it's very difficult to see because you just have so many events in the small surge, but close to New York City category. Now, we're going to do one last thing, because here, this is all tracks. So there's no subsetting based on the sea level pressure or the wind. If we conditionally subset so that we're only looking at the storms whose winds exceed 18 meters per second, so the stronger events during the time of surge, and now expand our search radius, we're able to start to see differences between the tracks that cause the biggest surge and those that cause the smaller surge. And these differences relate to both the orientation of the track. So these tend to have a hooking pattern, all right? And for reference, there's the 1950 storm that was on the title slide. There's one other storm that takes a similar hook. But a lot of these storms have something forcing them back to the west, whereas those that meet all qualifications except creating large surge instead don't have any sort of westward component to the path. They're zooming off to sea. And in fact, if we look at the cyclone center speed for these, it tends to be larger than the speed for these. So they're moving through the region faster. Last part of the analysis is to consider bomb cyclones. As a reminder, so bomb cyclones are extratropical cyclones in which the central pressure decreases by at least 24 hectopascals over 24 hours. And this gets normalized by a specific latitude, and it corresponds to a metric called a Bergeron. And Sanders and Joachim paper look at the climatology of these events. I'm going to consider the strongest bomb storms for our region. So these are the ones that dropped 20 or 48 hectopascals in 24 hours, or 2 Bergerons. And it has that deepening has to occur south of 55, right? So these are storms that are bombing out in the Gulf Stream region. And over here, the pink represents their surge versus distance. And what you can see is that these strongest bombs events are rarely those that cause strong surge. If we limit ourselves to the moderate bomb events, and it's not a few events, okay, there's 407 events in this 70-year record that had a deepening of 1.5 Bergerons, or 1.25 Bergerons, which would be 30 or 36 hectopascals over 24 hours. In this case, you can see in terms of distance and surge created, we're capturing some of the biggest events, but overall, there's no increased likelihood of a bomb storm causing the strongest surge events. That's a typo. Pardon me. This is real time, sorry. The bomb cyclones are not the most likely to cause surge, which is in accord with the results from the Catalano and Broccoli study. They argued that it's less about the cyclone itself and more about the upstream conditions. These are the conclusions. Okay, so in regard to the first question of the relative role of tropical cyclones and extratropical cyclones generating surge, the TCs are most likely to generate the extreme surge. However, the majority of strong surge are created by extratropical cyclones. It's true for the mid-Atlantic and the Northeast. Question 2 was, can the variability of strong surge be explained by variability in characteristics of storms? The answer from the observations we analyzed is yes, but it's conditional upon the distance of the cyclone to the impact region. And for extratropical cyclones, the fastest strengthening storms are not the ones most likely to cause strong surge. And even the moderate storms are no more likely to cause strong surge than non-bombs, all right? And so that's it, and I can take questions. Thanks for your time.
Thank you very much, James, for a really interesting talk. Do we have any questions?
I have a question. So I find following these tracks with the eye is really challenging. Have you thought about making like a heat map, like one day ago, and just to have a gridded map of where all the centers of these storms were, or where all the centers were 2 days ago, and maybe it would be easier to pick out patterns? Because I don't know, maybe it's just I'm not used to looking at the squiggly lines.
So what we usually are looking at is 6 hourly locations, and so I think it kind of links up with the heat maps. There are studies for windstorms in Europe where instead of using the tracks, they use a cluster of strong winds. And we did that actually in the wind analysis paper, and what we found there was that there's usually a nice relationship between where the storm is going and where the wind is. So I would say I appreciate what you're saying, and my hope is that instead what will eventually happen is, and what probably could have happened this time too, is that at the beginning, when I introduce the tracks, we'll have a large set of literature showing where the hazards tend to be for certain tracks. Does that make sense? I can see it. I can show a nice example of this actually. Let me just stop sharing for a second. So for snowstorms, there's been some studies, a couple of analyses where they tried hard to match up where the snow is when the path is going a certain way. So let me just bring up that diagram, and it'll get it. I think it may be matching up with what we're thinking about. Okay, so this Changyan et al. Study, what they were able to do is look at a bunch of tracks creating snow and then say, where's the snow most likely to fall? And so they have this diagram that gives you this nice picture of, okay, when the low's here, here's where the snow is, heavy snow is more likely to be. And so we have this same sort of pattern now in play for winds. And we wanted to get something similar for surge, but it does not seem to exist.
Do we have any other questions from anyone?
Alan would like to ask a question to Jimmy.
Okay, great.
Okay, so Jimmy, we have all these wonderful models, parametric models of tropical cyclones. Do you have any thinking on extratropical cyclones and how we could sort of parameterize that in a way that we do the tropicals?
Yeah, so my thinking is that we need to use the wind direction guided by location of warm and cold fronts. And so I think that the parametric model that could potentially be built would need to focus on the time evolution of the frontal location relative to the storm center. And then from that, just be able to back calculate wind direction. One parametric wind model for extratropical cyclones that I know of was built at SUNY Buffalo by Wu Tang. But that model seemed to be more of an evolution of what TCs are doing rather than built from scratch for ETC geometry. But with the fronts, what I'm thinking about is that between the warm front and cold front, in what we call the warm sector of a storm, we know that the direction of the wind is unique from the rest of the region where it's a bit more, the wind is more annular or circular around the storm. So we'd be able to put wind direction in without having to model so much if we were just modeling a time evolution of the fronts.
Very interesting and a very nice talk. Thank you.
Oh, sure. Thank you.
So Philip Orton has posted it's Tim Hall's paper, I believe. Philip Orton has posted a reference in the chat.
I was just posting your paper, Jimmy.
Right.
On synthetic tropical cyclone model.
Oh yeah, thanks.
Credit
That's
where
right.
credit.
Yeah, so with Tim, we have looked at extratropical cyclone tracks generated using a statistical model. And we call it synth-ETC, and this was published in 2018 in Hall and Booth and Journal Climate. And so with this one, we don't get yet winds, but we get extratropical cyclone intensity and path. And so we can, this is our starting point on which we would like to build the parametric wind component. This figure here, the red shows kind of the average path of a cyclone based on historical data, and then blue shows actual events, and then the gold is 1,000 track simulations from there. And so this evolved from the Hall and Jusen work on tropical cyclones and Hall and Yanakura work, or Yanakura and Hall, to the point. And what we did is we built one for extratropicals.
Do we have any other final questions? We're a bit close to the 12 o'clock noon mark, so perhaps we should close off soon. Okay, I'd just like to thank you again, Jimmy, for a really interesting talk.
Thanks, Jimmy.
Yep. Thanks, everybody. So this work is presented as a combination of stuff published and then stuff